to start our colloquium. Today, I'm very honored to have Professor Wen-Hao Chang from Zhaotong University to give this colloquium talk. Let me very brief just introduce Professor Zhang. It's actually very simple. He went to this Department of Physics at the Central University in 1994. Then he got the bachelor degree, the master degree, and also the PhD degree in the same institute. And after obtaining his PhD in 2001, he spent 4 years as a postdoc in also the same institute. Okay, that is because this military substitute. Okay, so today his expertise is in semiconductor. So today he's going to share his research on this 2D semiconductors, these opportunities and the challenges. Okay, let's welcome Professor Zhang.
Thank you for your invitation and also introduction. So actually, my CV is very simple. So I spent a total of 15 years in National Central University. After that, I moved to Zhaotong University. I also spent 15 years there. And so it's about time to move. So I recently, this month, I just moved to Academia Silicon. So I moved to Research Center for Applied Science. So I don't know whether I will spend another 15 years there. But anyway, so I got a new job because now Academia Silicon pay my salary, so I have to mention this is my new affiliation. Okay. I think today this is a colloquium, so I think maybe most of you are not in this field. So I will give you a very short introductions, and then maybe give you some overview to explain why we need to find new material, or more specifically, the 2D semiconductors. And maybe you would like to ask, actually now the semiconductor technology is good enough. Why we still have to find new material and to boost the performance of the devices? So I will give you some idea of why we have to do so. So let's start here. This page shows you how science and technology drive the societal change. So in 19th centuries, actually the most important invention is the steam engine. And at that time, people start migration to city. And in 20th century, the most important invention is the internal combustion engine, and also the electrification, and the trade become international, and also urbanization. And in 20th century, right now, the most important, so we cannot deny, the most important technology is semiconductor technology, and also information technology. So now because of this technology, we have globalization, and now economy has information, knowledge, and service-based technology. So what is our future? Our future may based on many new technology like IoT, and also AI, and also self-driving car, and so on. So maybe you will find out, actually our future relies on huge amount of calculation, because IoT, AI, also self-driving car. Actually, now the self-driving car still, the calculation, the efficiency is not good enough to, so now the battery technology cannot afford this kind of calculation. So So in the future, if we want to have this kind of life and technology, so we have to improve our devices to have higher efficiency and also lower power consumption. So improvement of devices technology is still very important, must continue. So that's why we have to find new technology. So this is a semiconductor logic technology. So we know 40 years ago, we went from micro scale devices to now start to sub-micron to nanometer scale. So actually the technology almost stopped at 10 nanometer, but we have a very big, very good company in Taiwan. They further pushed to 7 nanometer to 5 nanometer. This is TSMC, we say this is 护国神山, right? So, but why they can do so? It actually enabled by many, many new technologies, like EUV lithography, and also new transistor structures, and also new gate material, and so on. So in the future, what is next? So if we extrapolate, can we move to zero nanometers? So maybe you think you are living in a wrong eras, because when you go to TSMC, you have to face the 0 nanometer technology, right? So I think in the future, technology below 5 nanometer node must be enabled by new materials. This is also the roadmap of TSMC also. So 2D material is an option, one of the options, but they are still finding some other technology that can continue the device scaling. So let's see what is the problem when we try to scale down the devices. This is a typical so-called MOSFET, the field effect transistor. So if you try to scale down the FET like this, you will face a problem of so-called short channel effect. What's the short channel effect? In this typical FET structure, you have source and drain and the gate. So the operation mode is that you can use gate to control the channel here. The channel here. So you can control the conductivity between the source and drain. So it operates like a switch. So typically in the so-called long channel field effect transistor, the channel length is large compared to the so-called the depression width of the semiconductor. So it acts like a nearly two-dimensional conducting channel with electron or hole in this interface. But you could try to scale down the gate length like this. So in this case, the channel length become the same length scale with the depression width. So it becomes non-uniform, and then you will cause some so-called short channel effect, like the drain-induced barrier lowering, and also velocity saturation, threshold voltage variation, and also degraded substrate performance. This is some problem associated with the device scaling down. So how to solve this problem? The engineer tried to solve this problem. They try to use a thinner material. So they try to thin the silicon to become a very thin channel, so you can eliminate or reduce the effect of short channel effect. So maybe you know this technology. This is so-called FinFET technology. This is invented by a Chinese professor in United States. And these structures is also take the advantage of very thin materials. So they fabricate like a fin, and this is a source and a drain and a gate cross at the middle. So this is in this kind of structure you can reduce the short channel effect. So if you want to reduce the gate length, you have to reduce the thickness also. But so this is now the FET structure roadmap. Conventionally, we use so-called planar structures with soft drain and gate. And then we move to so-called FinFET technology with very thin material at the middle, and this is gate material. And now, if we want to try to push further into the 5 nanometers or even 7 nanometer technology, so now they try to use the so-called gate-all-around structure like this. So this is channel, and so the gate is surrounding the material. So you have to reduce the material size at the same time. But what's the problem with if you further thinning the materials? So this is the problem, because if this is mobility, this is channel thickness. If you want to further reduce the gate length, then you have to thinning down the thickness. So you can see the material, the electron or hole mobility become smaller and smaller, and eventually it doesn't work. Why it doesn't work? Because the silicon material, this is a 3-dimensional crystal. They have some surface state and may trap some charge at the surface. So if you reduce the thickness to, for example, down to 3 nanometers. So down to 3 nanometers, the electron will see many charge trapped at the interface, and the Coulomb potential will block the electron to move. So eventually, the electron cannot move in very thin silicon. That's why we have to find new opportunity. So 2-dimensional material like this, you may heard about this for many times. So like MOS2, this is a 2-dimensional material. Because this kind of 2D material has no dangling bond at the surface. So carrier can move freely in this kind of material. That's why. And then the thickness only, the ultimate is 1 monolayer. 1 monolayer only about 0.7 nanometer thick. So this is a good, very good opportunity for very thin FET structures. So let's check the mobility. You see, this is MOS2, MOSE2, or WS2. This kind of material actually, they have much better than silicon at the same thickness. So once you want to reduce the thickness, 2D semiconductor is a very good opportunity in this. So actually, we have many different kind of 2D material, like graphene, bright cluster, and so on, and also boron nitride. This is insulator. So this is a band gap. So typically, the material in this range with a band gap of about 1 electron volt is very suitable for electronic device, because this is also similar to the band gap of silicon, which is also about 1 electron volt. So now many researchers try to use like MOS2, MOSE2, so-called transition metal dichalcogenide. This is a kind of 2-dimensional semiconductor. They are layer materials with very weak interlayer interactions and no dangling bond, and the force between the layers is van der Waals force. So you can separate this kind of layer material and maybe control the thickness down to only 1 monolayer. So now the most commonly seen semiconductor is MOS2 and MOSE2, WS2 and WSE2. These 4 materials are the most commonly seen material, TMD materials. So they look like also have this kind of honeycomb structures like graphene. And how to obtain this kind of 2D material? as you know, we can exfoliate from bulk crystal and also use CVD growth, like today I would like to show you. So in this way, you can, it is, I say unlikely, actually it is impossible. You cannot use exfoliate in TSMC. In TSMC, use exfoliation to produce a larger scale electronics, right? So you have to, anyway, if you want to have industrial application, all the technology have to has to be scalable. So you can use this technology to fabricate wafer scale and also to a larger scale device fabrication. So now we can use like CVD growth to grow the material on 2-inch wafer. And actually, this is limited by the size of our CVD system. So the TMD materials, 2D semiconductor, also has some other interesting property. Like, for example, it typically is a multi-layer. When they are multi-layer, they are indirect semiconductor. But when they reduce thickness to only one monolayer, they become direct bandgap material. And they also have very interesting, very unique electronic band structure. Like they have conduction band and valence band minima and maxima at the K value, and they have some spin splitting, some spin structure, which is reversal in different kind of values. So researchers try to use this kind of band structure to perform so-called valuetronics. So provide another degree of freedom like spin to become spintronics and also valuetronics. So physicists is very smart. Say any degree of freedom, they can become broadtronics, right? So pianotronics, spintronics, electronics, anyway. So if you find some degree of freedom is useful, you can develop your own broadtronics. Okay. So 2D semiconductors now have many new opportunities, like for 2D electronics, 2D photonics, 2D sensors, and also to explore some new physics in two-dimensional systems. So the opportunity is that now we can use this kind of semiconductor material to fabricate electronic devices with very good, very high current on-off ratios, and also maybe they can solve the short channel effect for 5-nanometer node technology. And for photonics, this is direct bandgap, and also have very large exciton binding energy, up to half electron volts. This is in typical semiconductor, the binding energy is about a few milli electron volt to a few tens milli electron volt. But in this case, it's half electron volt. It's very huge. And also have very strong light-matter interaction, and also very large optical nonlinearity. And also for sensors, because the material has very high surface to volume ratios, and also they are easy to transfer charge with the environment. So if you attach to any metal or attach to dielectric material, it will occur some carrier transfer between the materials. So it is very good for sensor. But on the other hand, something can be a sensor means that this material is not stable. Okay. And 2D physics is a very unique optical selection rule, and also have some coupled spin value physics for spintronics, valuetronics, and also can have new exciton physics in the 2D system. But we still have many challenges, like the material quality issues. Now we're still trying to grow single crystal, large area, up to wafer scale. And also low carrier mobility, metal contact, and the dispersion, and also very in 2D photonics. Actually, the low quantum year is still a big issue in this field. And also the very short photo carrier lifetime. And also now we still don't quite understand the process of exciton formation and also the axial dissociation process into the material. So we still need some new experiment to understand the underlying mechanism and process. And also for sensors, the stability, reliability, sensitivity, selectivity is still problem. And also for in the physics, spin and spin valley depolarization, and also how to electrically inject carrier with valley polarization or spin polarization, or how to use electrical detection. All of these are problems, so still have many challenges. So our group at NTU, now we are trying to synthesize high quality wafer scale. So later on I will show you what means high quality. High quality means a very low defect density. So now we can control to some level of very low defect density, and also the wafer scale to the semiconductor. Also, we are trying to explore some new material with better or good carrier mobility, and we are trying to solve the metal contact, because typically the contact resistance is very large when you use a typical metal contact with the 2D semiconductor. This is the major bottleneck to realize practical electronic device for industry. And you may know we were working on the hexagonal boron nitride, the growth, and we also have try to fabricate some 2D heterostructures. So today I only talk two topics. One is growth. So the first material growth. I will show you how to use the CVD growth to grow this kind of highly oriented material on sulfide substrate. And another one is we try to grow material on metallic substrate. And I will give you three examples. This is boron nitride on copper 111. This is MOSE2 on gold 111, and this is PTSE2. And the second topic is 2D heterostructures. So we take the advantage of CVD growth, so we can grow so-called commensurate vertical bendable heterostructure. And this is not possible to achieve by mechanical stacking, because mechanical stacking you cannot control the atomic registry down to atomic scale. So you may form some Moiré superlattice. But on the other hand, we also use CVD growth material to stack to form the so-called Moiré pattern, and they can produce some new phenomenon in this so-called Moiré superlattice. So this is our CVD lab in NTU. So we have many CVD systems. So maybe you have 12 or 13. So they are growing different kind of material, and I usually say not chemical vapor, it's a cash vapor. So every day you deposit cash. So maybe you think CVD, usually we consider they are cost-effective way to grow material. But if you have too many, that's become cash vapor.
How you pass the safety check?
Okay. The first one, we try to grow on sulfide substrate. So typically, this is simple. You just put some precursor like moly oxide and selenium powder, and heat up. So you heat up, then the vapor will deposit on the substrate. So typically, we use the sulfide substrate, and the blue one is the TMD material, like MOS2. So you can see some triangular grain and randomly oriented on the substrate. But if you carefully control the growth condition, you can use the sulfide surface lattice to guide the growth. So you can see it's upstream, middle stream, and downstream. So you can see this grain, they have the same orientation or the opposite, but they are not random. So in this way, when they stitch together, will form continuous fin. That still have some grain boundary with like this mirror twin boundary. So actually they still have some grain boundary. But in this case, the film quality is much better than this kind of randomly oriented grain to form a continuous fin. So now we can grow 4 kinds of material. All of them are highly aligned. So you can see they are aligned the same or the opposite direction. So MOS2, WS2, MOSC2, and WSC2. And then we can control the defect density. So maybe I will show you later the STM result, but here I just show you the low temperature photoluminescence. If you are working on this field, you will know if you cool down any CVD sample to measure the photoluminescence, you will see a very, very strong defect emission, not the external emission. But in this case, if you improve the material quality, reduce the defect density, actually the spectrum will be dominated by external trials and a very weak defect emission like this. This is defect emission. This is the external trial. The external trial very low defect emission. So this is not easy. So typically in CVD sample, the low temperature PO only show defect emission. And this is the opposite spectrum. You can see the valence spec. But remember, this is a conventional optics. The beam size may be millimeter size, or maybe 200 micron. Very large scale. So that means that the grain orientation is highly oriented. So you can measure the angle result photo emission spectrum to measure the band structure of the material. So typically, if you want to take this kind of spectrum, you have to use so-called micro optics and to measure only single flat. But in this case, the resolution and also the signal to noise ratio is very, very poor. We also use our 2D CVD material to fabricate FET. Well, this is a typical example. And as you can see, the mobility is about 10 to 20 for MOS2. But for WS2 is much higher. WS2 maybe 30 to 100. And the current on-off ratio is also very high. It's up to 9 order of magnitude. And also very high, it's a sizable current size. Current is about 25 micron amp per micron. So I think this is ready for developing FET devices for industrial applications. So the performance actually still have space to improve, mostly at the contact and the interface. So if we can solve this problem, actually we can further use this material in the back-end of line of the IC technology currently at TSMC. So the second one is we are trying to grow material on metallic surface. The first example is we grow hexagonal boron nitride. Maybe you know the hexagonal boron nitride is a layer material, insulator, and very important as an interfacial layer. If you want to fabricate 2D semiconductor as a FET devices, if you use boron nitride at the interface between the semiconductor and the dielectric layer, they can block the influence of the charge at the oxide layer. So this is very important material. But typically, this kind of material can be high quality material can be obtained by exfoliation. So we try to use CVD to grow wafer scale boron nitrides. So this is a example. We grow this material on copper 101. So you can see this is continuous film, this is individual frag, and this is transition region. But actually, we intentionally to grow such a large gradient to show this effect. Actually, the growth rate is very fast, so you can directly cover one mono layer in a full wafer. But we just use some technique to cover another substrate on top, so they will form a very large gradient to show you the grain orientation. Like here, you can see the grain only oriented in the same direction. That means this grain, when they merge together, they will form a continuous film without the grain boundary. Without grain boundary between different grain. So typically, in the past, actually, growth of boron nitride on copper is not a new method. It has been known for a long time, but they typically will form the so-called two direction. For example, they have this direction and also another direction. So this is a grain boundary of the copper. So if you prepare a copper substrate, but if they are not single crystal, you actually will have many different grain orientation, and eventually you cannot form a single crystal up to wafer scale. So the key is how to prepare a single crystal copper 101. So actually, you can buy a single crystal copper. As a physics guy, you may think you just buy it in the market, so you can do the experiment. But you cannot use this in TSMC into their fabrication line. So we have to use wafer. Everything is wafer. So if you want to deposit copper, we have to find a wafer substrate. So in this case, we use a sapphire as a substrate, and then we spotted a copper. But typically, you cannot deposit single crystal copper. So you have to find some way to improve the crystallinity and then eventually to achieve single crystal. So we use thermal annealing. That's quite simple. You just in a furnace and change the temperature and find the good annealing conditions like temperature, and also you have some gas flow like hydrogen, argon, and so on. So you can improve the crystallinity and become single crystal. So as you can see, this has some grain boundary, and the grain orientation is not the same. But in this case, they have only one direction. So the key is the substrate, not the growth. Okay. So this is the STM result. So you can see very clear the step flow of copper 101, and also can see the Mori pattern of boron nitride with the copper lattice, and you can also see the Mori pattern are actually aligned along across the step flow. That means the boron nitride actually stitching together and go across the step. So they form a continuous beam, even across the step. And then we can use some technique to exfoliate the material and transfer to another substrate. So this is the process and the image, and actually we use thermal rheostat, PMMA, and something very similar to what has been used in this field. So we eventually published this work on natural disease, but you already know the key. The key is the copper, not the bromide, right? Okay. So the next, this is some device test. We just, this is by the reviewer. The reviewer say you have to provide some evidence that your boron nitride actually have effect on devices. So we spend another 1 month to take this data and to convince the reviewer. Right? Another example is the growth of MOSD2 on gold 101. The gold 101. So you already don't know the key. The key is the gold, not the MOSD2, right? So we also deposit a thick layer of gold on sapphire, and then followed by thermal annealing. So if you use a lower annealing temperature, you can see very porous grain, and up to 1,000 degrees C. So you can see the crystallinity become much better. So this is electron beam, electron backscattering diffraction. So you can clearly see this direction is, I'm sorry, this is 101. So this is 101 directions. And also you use atomic force microscopy. The surface is very clear atomic stack. So this is a very clean gold 101 surface. And also we use low energy electron diffraction. You can see very clear hexagonal spot. The beam size is millimeter scale. So actually this is the natural orientation is the same. Crystal has the same crystal orientation. So after prepare the single crystal gold surface, I have to say, if you deposit wafer scale up to 1 micron gold, it's very expensive, right? But I'm not telling you I'm very rich. I usually send the substrate to TSMC and say they deposit and then come back. We use and so the goal is TSMC. So if you buy TSMC stock, make sure you pay all the money to my gold. Okay. We grow MOSD2 on gold 101. So you can see I show you this is a darker area is MOSD2, and this is a gold surface. So you can see the grain boundary. Actually, I highlight here, they are parallel. So actually, they are guided by the gold 101 surface. So when they merge together, they can form large area, single crystal, MOSD2. And we also use SDM to check. So similar to hexagonal boron nitride, they will form Mori pattern. And also, we use the lead pattern. You can see the MOSD2 crystal is also very clear hexagonal spot, and also some Mori pattern features in the lead pattern. So it is clear evidence that the material is large area single crystal material, MOSD2. And we also try to use STM to identify the defect density. So as you can see in the image, this is an atomic step of gold. So you can see this darker area, this brighter area, and you can see this is a atom of MOSD2. So you can see here, we have one defect. This is vacancy. Another defect here. And if your eye is good, here is another. So we all have 3-point defect. So if you calculate the area, actually the structure defect density is about 4 to 10 to the 11. So this is quite low. Typically, it's much higher than 10 to 12, or even 10 to 13. But in this case, this is quite low. Okay. The third example is we gross PTSD2, also on Go 101. So the story is the same. So I don't need to repeat. So actually, PTSD2 is not easy to nucleate on such as sulfide crystal. So it usually shows some island growth. But on Go, it will form larger flat with only monolayers here. So we have some characterizations like use SEM and also STEM atomic result. So you can see PTSD2 is 1T phase, and the lattice is about 0.37 nanometers. And we also show from cross-section STEM, you can see very clear PTSD2 layer and a Go. And they also have some align. For example, if you have 4 platinum atoms aligned with 5 gold atoms. So this is a kind of commensurate stacking. And we also use STM. You can also see Mori pattern with the same orientation. So if you stack PTSD2 on gold surface, actually you will find A by A structure will almost match with 10 by 10 gold surface. And in this case, the strain is about 3%. So if you gross the material on gold surface, this is some strain on the surface. Okay, this is the first part is gross. Okay, so we also use this material to fabricate devices. So we also try to do some local layer engineering. That means monolayer in this material is very unique because PTSD2 is semiconductor when they only have one monolayer. But theory predict that for 3 layers, this material become a semi-metal. So this is very good for to improve the contact. If you you can engineer the thickness of the contact area. For example, we have a semiconductor here, one monolayer, and then we use lithography to try to increase the thickness. How to do that? We just deposit platinum at the contact area and followed by sterilization. Yeah, the temperature is not high, just about maybe 300 or 400 degrees C in the selenium environment, and it will convert platinum into platinum dicellulite, and then we deposit metal. So you can use this way to improve the contact resistance. So this is also can be applied to electronic devices. So we still have some time to move to the second topic. Very short. Don't worry. 所以我们是到几点？15到20分。15到。So I still have 10 minutes. Okay. This is 2D instructions. You know, 2D material can form this kind of vertical heterostructure that we call this van der Waals heterostructures, and also this kind of lateral heterostructure. But this kind of structure you can use in mechanical stacking, but you cannot use stack stitching this kind of material. You can only use growth. So basically, this kind of lateral or vertical heterostructure, you can use different precursor and use different temperature to control. For example, if you use higher growth temperature, you typically will form vertical stacking of different material. But if you use a lower growth temperature, it typically has a lateral heterojunction. So if you stack 2 different TMD material together, typically this kind of material has so-called type 2 band alignment, like this. This is one material band gap, and this is another band gap. And then they have this kind of so-called type 2 band line. That means that if you have electron and hole in the two material, electron will jump to transfer to one layer, and the hole will separate to another layer. So electron will and the hole will separate at two different layers in this case. So we call this is so-called interlayer exciton. And now if we stack two materials together, you have two different situations. One is so-called commensurate. Commensurate means that all atoms will stack perfectly with a very good atomic registry like this. And the other one is if we have some interlayer twist, or the two material has a little bit lattice mismatch, it will form this kind of Mori pattern with periodic variation of the atomic registry. So we call this pattern as a Mori pattern or Mori superlattice. So this kind of commensurate vertical heterostructure, you can only use growth. You cannot use stacking to form this kind of structure. And in this case, because we can use this kind of structure to study the how the atomic registry affect the interlayer coupling. Like for example, the interlayer separation, the band gap, the band offset, and also the selection rule. Also the hybridization are very sensitive to the atomic registry between materials. And the Mori, when you have a Mori pattern, like Mori superlattice, so you will have spatial variation of atomic registry. So this atomic registry will also have some spatial modulation in the band gap. So you will have potential modulation for the electron or hole or for exciton. So you artificially create a superlattice for electron hole or exciton in this case. So we can use growth to control this kind of lateral or some vertical structure with at the center. Like here is a vertical bilayer structure. This is also bilayer structure. And we also asked Zhu Mingwen to provide stamp images. So he confirmed that this is commensurate structures with perfect atomic registry in the bilayer. So we can have so-called R-type stacking with the same orientation, and this is H-type stacking with the opposite stacking. So with stacking angle is 60 degrees. So we found this material can have very different optical selection rule in comparison with monolayer case. But I think I don't need to go through the detail. So we also found the two material can, in a commensurate bilayer structure, they will produce some interlayer hybridization. For example, this is, you can see in H-type. Here we can see some splitting here, and also here has some splitting. That means the idea is here. This is conduction band, band span, and in band span we have spin up band and spin down band. This is another material with a little bit different band gap and offset. So the two material roughly align with different spin band at the interface. So if you have so-called R-type stacking, actually these two bands will not hybridize. But if you change to H-type, the two bands become the same spin. So they saw each other and they become hybridized. So they will form bonding and anti-bonding state. So that's why we can see some splitting here, which correspond to the hybridization strength of this band. And this is I just introduced some commensurate case, but for the case with the Mori pattern, the periodicity will change with the twist angle. So in the past few years, people try to study this kind of bilayer system with Mori pattern, and found very many interesting phenomena, like unconventional superconductivity in bilayer graphene. This is very famous in the past 2 years. And also in TMD material, we can use the Mori pattern or Mori superlattice to moderate the exciton dispersion in the material, because we impose another periodicity to the exciton or carrier. And they can also create some so-called topological state in TMD bilayer with Mori pattern. So we also use our CVD growth samples to study the so-called Mori superlattice and their effect on the Mori miniband, Mori exciton effect. So let's go a closer look at the Mori supercell. So you can see they have some high symmetry point, and they correspond to different local atomic registry. That means you have different registry, and also means you have different interlayer interaction or interlayer coupling. And the interlayer coupling will change a little bit the band gap, so you will form a potential modulation like this. So why the superlattice will affect the exciton behavior? For example, this is a dispersion of exciton center on mass motion. This is kinetic energy, and this is the momentum. And if you introduce a Mori potential here, then you will create so-called zone folding, like you study in Kittel solid state physics. Kittel say you can fall back to form this kind of new miniband, and at the zone edge you will form some band gap open because of Bragg reflection. Yeah. So if the potential modulation is small compared to the kinetic energy, actually the band gap opening is very close to the potential modulation. But if the potential modulation is large compared or comparable to the kinetic energy, it becomes the dispersion will become very flat, and it will be pushed downward to form this kind of miniband. That means if you can control the potential modulation, you can modulate the exciton energy like this. But it is not easy to control the potential, the amplitude of potential modulation. But you can change the periodicity. Now, you change the periodicity, actually act the same behavior, because for smaller periodicity means that you have larger kinetic energy at the zone edge. That means that the same potential modulation will be small compared to the kinetic energy. On the other hand, if you use a large superlattice, then it becomes the zone becomes very small, and then the kinetic energy also small. So that's why we can use twist angle to change the periodicity, and then it changes the relative amplitude of the Mori potential to the kinetic energy. So you will see different kind of energy modulation to the exciton. So typically the periodicity inverse proportional to the twist angle, and also the lattice mismatch. So this is in lattice match case. So when you use a very small angle, it becomes very, very large. The periodicity can be very large. And this is for lattice mismatch case. So if you change the twist angle to 0, it pins the periodicity at about a few nanometers. So this is a typical image of the Mori pattern. So you can see there can form some irregular Mori pattern because if you mechanical stacking, if you have some structure defect, you will form this kind of, so this area is very regular, but here it becomes irregular. So it is not easy to have long range and a large periodicity to keep this kind of large periodicity. So it's not easy, especially for optical measurement, because the optical beam size is in micron scale. So if you want to study the periodicity, how the periodicity affect the electronic behavior, you have better to use a lattice mismatch system like this. So last year, actually on Nature, they already published about the so-called Mori acetone in this kind of heterostructure. But they failed to reveal how the Mori periodicity affect the excitonic state. So because this is, if you want to study this, you have to fabricate many devices with different twist angle. So be honest, this is very tedious, and the yield is very low. And so you have to hire many graduate students to do the same thing. And then sample to sample variation will let you feel very frustrated. And now you give up. So now we use another approach. So our approach, we take the advantage of CVD. So like we can growth, for example, we growth highly aligned materials, and then we stacking the two materials together. So at the same time, we can use one larger frag to stack on another. So you can form many like similar twist angle frag. So you can study this kind of spectrum at the same time, fabricate once, and then we can take many heterostructure at the same time. So we can study this kind of heterostructure, and I just give some. You can see some spectral change. You can see we can have many data points across from 0 degree to 60 degree, and we can study the angle variation to see how the periodicity affect the excitonic dispersion. So we also use some theoretical model to model the Mori acetone, but I think this is very detailed, so I think we can skip this. We also try to use DFT calculation, and we found very interesting is that our experiment result predict that actually the potential modulation could be up to 100 millielectron volt, but for DFT calculation, they only predict very small potential modulation. I think still have some discrepancy because in DFT calculation, we didn't consider the structure reconstruction because of this is a lattice mismatch system. They may have some strain at the different high symmetry point in the Mori supercell. Actually, we also have some data to confirm that the Mori potential is very large in this case. Oh, anyway, I don't think this detail is very important. Only important to us, but not important to you. So this is summary. So today I introduce our effort on the 2D material growth, and we growth on sulfide substrate, and now we are trying to use metallic substrate to grow 2D material. And then we also study 2D heterostructures, and recently we are interested in to study how the Mori pattern and the Mori superlattice affect the electronic structures and also acetone optical property of the acetone 2D material. Thank you very much for your coming. Thank you.
Okay. Now the floor is open for questions.
Okay, on the first part, for the growth on the metal, could you also give some remarks on, let's say, why copper 111 is chosen for boron nitride, whereas gold 111 is chosen for another?
That's quite simple, because copper is cheap, but they will interact with chalcogen atom.
Okay.
So you will form copper sulfide, copper ceramic. So any other metallic substrate will interact with the chalcogen atom. Only gold.
Okay.
Only gold can sustain in the chalcogen environment.
Okay.
Yeah, so that's why we have to use very expensive substrate.
So, so after all, you're going to transfer into other substrate.
Yeah,
for
sure.
device. Okay.
Sure.
Actually, you already made a very short remarks on the strain effect on all the heterostructure, no matter what they will have.
Yes.
Due to the fundamental lattice mismatch.
Yes.
Another thing is that perhaps the thermal expansion mismatch is also contributing.
Yeah.
Uh-huh.
Yeah, I understand. Yes. Thermal mismatch will occur, especially we use a very high growth temperature, especially use in sapphire or oxide. But for metal, because I think our growth temperature is quite high, and especially it's approaching the melting point. So I think, I'm not sure, but maybe the mismatch is not the very important problem. Yeah.
Thank you very much for this very interesting talk. I was wondering about the platinum selenide.
Yeah,
you were showing that making thicker contacts will improve the contact resistance.
Yes.
What's the uncurrent that you're getting? Because in the end, you will have to squeeze out another 10-fold increase in uncurrent if you want to be compatible with FinFET. Currently, you have 25 micron. You have to get to at least 250, maybe 500 micron per micron to be, fighting with silicon. So, but you were saying that's a problem of contact resistance.
Yes.
So, is the platinum selenide contact resistance significantly better than the MOS2 you were showing?
In this case, if you increase the thickness, actually yes, because it is semi-metal. The contact resistance can be lower than maybe now typical in MOS2, maybe a few hundred kilo ohm micron, right? But they can reduce down to below kilo ohm micron. Below kilo ohm. So this is very promising.
And what's the mobility of the
The mobility is that in monolayer PTSD2, now our mobility may be 6 or 10 around this
room
range.
temperature or room temperature?
Room temperature, yes. Room temperature. Do you satisfied?
There.
Anyone? Okay.
Yeah,
sure.
thank you. Thank you for this very nice talk. I mean, even I'm not working on 2D material, but I learned a lot today.
Thank you.
Right, so I understand the impact is mainly you grow aligned monolayer of TMD material and the mass compatible with mass production.
Yes.
However, during this presentation, I don't understand why, because you initially show the growth is from this
Small
triangle
yeah.
cells, and then you grow the extension of growth link these small cells.
Yes.
But I don't understand why they only form monolayer, because it's vapor deposition, right? So why there's no multiple layers, only monolayer?
Yeah.
Yeah.
Good question. Actually, if you grow the material on oxide, for example, on sapphire, and if you tune the growth condition to growth monolayer, typically you cannot grow the second layer, because once you form a very good monolayer on sapphire, it is very difficult to see the second layer on top, because they don't have dangling bar. But they can be very easily to be sit on sulfide surface because sulfide surface has some dangling bond. They will trap the atom. But this situation is similar to graphene. Yeah. No dangling bond, no surface bond, so it's hard to sit any other atom on top to form another. But if you growth condition improve, all your CVD is very dirty, you easily form different kind of layer.
Yes. Okay.
Yeah.
Okay. The second question is about this boron nitride grows on metal. Sorry that I didn't catch why it is necessary to grow boron nitride on metal instead of on sapphire.
Because we are unable to grow on sapphire,
Okay.
so we use copper is actually it can be considered a little bit catalyst, but in this case, they also depend on the solubility of the material into the metal. So for the case of boron and the nitrogen in coppers, all the solubility is very low. So the growth actually is self-limited, will grow only one layer. But for some other metal like nickel, the solubility of boron and nitrogen will be higher. So if you grow the material on nickel, you typically form multi-layer.
So this knowledge comes from experience, or is there some underlying theory?
Theory,
Experience.
Okay.
Yeah.
I'd like to ask the question of the current status of the defect. I mean, no matter what you do, it's nearly perfect, but still, can you give us some sort of state-of-the-art defect? For instance, in silicon, we know it's way below 10 to the 6, but in this per unit area,
Yes.
what's the number currently?
What's the number? The state of the art?
Yes.
The state of the art is the state of the art is this value.
Okay. So
This value is the state of
it's
the art.
current.
Yeah.
So what's the acceptable for TSMC
Yeah.
if they really want to make
10 to 12. 10 to 12. So below this is good.
Okay.
Yeah.
Oh.
This is good.
The milestone is 10 to 12. So
Okay.
we already achieved.
It's
Yeah.
far less than silicon. Silicon is 10 to the 6, so even
10 to the
less.
6, but this is 3D.
Right. Per,
Per micrometer
This is
square.
surface defect density of
Surface
10 to the
defect
6
density.
per
Uh-huh.
centimeter squared.
Yeah, I
so
think
for silicon is 10 to the 6.
Yeah.
So
And
why
gallium
2D
arsenide
can
is 10 to the
tolerate? Yes, gallium arsenide is also very low.
Yeah.
So why 2D can tolerate?
But I thought this the typical defect is the vacancy, right? But actually, sulfur or selenium vacancy cannot exist in the surface. They always passivated by oxygen. But in the case, oxygen will not produce a band gap state. So it only have a little doping effect in this case. So not very serious.
Also one more, I'm sorry, maybe it's still a first, but
So if you want to do film, you have to transfer it off, right?
Yes.
So after transfer, how much increase of this defect density do you expect?
I don't know actually. We didn't test, but we need to test this.
There seems to be a very important question.
Yes, it seems to be very important. But we have to achieve low defect density for us-grown sample. But after that, we can try to how to use a non-destructive method to transfer the material. Yeah.
The other problem is for this wafer scale single crystalline film, do you see any domain boundary like the FCC type, the kind of stacking?
You mean metal or
the film?
the film?
For nitride or these TNT?
Actually, no. We didn't find any. So we cannot find the domain boundary by STM.
Naturally, you cannot expect all the nucleus will have perfect registry. So
Yeah.
somehow they just, when they meet, they just maintain a good registry and then relax the strain profile on the long range scale. That's probably consistent with this variation of Moree pattern at the same time.
Yeah. So I cannot answer your question because we expect they have, but we didn't find it. so I have no way to answer your question, but I think we expect they may have some grand boundary, but we already mentioned many different areas, but we didn't find it. So sometimes we claim this is single crystal.
And then still
Chen
ask one
Lao
more.
Sư, Chen Lao Sư.
I have a very naive question. When you say your experimental data is not consistent with theoretical calculation, so what the reason that you so confident that the theoretical calculation is not enough, and then your experimental data is correct?
Okay. Typically for band structure calculation, for example, maybe on Go also, I think DFT can predict very precisely. But in the case of Moree, with very large supercell and also with lattice mismatch, actually DFT has some limitation because we have to include too many atoms. So sometimes they have to use some technique to reduce the calculation. So maybe they can use some approximation or assumption. So that's the first principle. Right?
But about the theory physics, they may say that your experimental data may some other effect you don't take into consideration.
Maybe.
Like the Guangli said, probably there are so many theories in here. Yeah, you want to say?
So you want to say something?
It's somehow Professor Chang wanted me to say something. Well, in this case, I agree with the speaker. Because he rightly said that gold is metal and DFT prediction are quite good. But it happened for this Moree is semiconductor, and it's well known. Current DFT calculation cannot give a correct band gap.
Yeah.
And I think potential is at electron exciton C is due to band gap.
Yes.
Yeah, so I think although you want me to say something, I think
But they still have some limitation.
According to my understanding, DFT cannot predict
Anyway, I win.
any scale.
Okay.
I win.
One epsilon volt error.
Can I ask two questions? Okay. Last year I realized that, first thank you for giving very impressive talk. If you read many graphene monolayer paper, significant paper, you always note, I noticed even until last year, there are always two authors from NIMS, Japan. One is Watanabe. And then one day I asked Professor Shenjali, and he said that because this monolayer of graphene can only grow on very good boron nitride, okay? And this Watanabe group always provide this boron nitride to all the people in the world.
Yes.
Nobody else can do it.
Yes.
But now you say that you also grow this very good boron nitride. So did you get any people want your sample?
So request our boron nitride to grow graphene?
Yeah.
No, never. So that is maybe not good enough.
Very recent, you always notice Watanabe in co-author almost all these important papers.
But I have to say, in that case, they need to use multi-layer boron nitride or bulk boron nitride, because in this case, if you gross boron nitride on copper and you want to gross another material, actually they will see the copper, not the boron nitride.
Oh, okay. So
The copper has very strong interaction with another material.
short circuits.
Yeah, so they have some remote epitaxial effect with the bottom copper layer.
And second question is about platinum diselenide.
Yeah.
Okay,
You calculated that 30 years ago, right?
Oh, then when I was a student, but I'm wondering, I mean, molybdenum disulfide, all this direct band gap has a lot of interesting things. What's the advantage of platinum diselenide? Why you want to grow it?
The platinum diselenide, the key is that they have very strong band gap moderation with the layer thickness.
But I guess it's not direct band gap.
Yeah, but for electronics, it's nothing to do with direct or indirect. Yeah, for electronics, it's a very, for silicon it's also indirect. So it's a very good choice.
I have to ask. Okay, well, I'm a student.
Student, yeah, good.
Do you use the Wien equation to model the excitant?
To model exciton, right? Yes. This is this is linear wave function.
Okay.
Right? Good. Satisfied? Okay. Good.
Okay.
One more question about the details of the defect.
Okay.
I think you must have a lot of sample checked by the SPM.
Yes.
And although we also know the sulfur or selenide is the one to leave the surface, even during the high temperature process.
Yes,
so that's why most likely there will be a lot of vacancy. But if the vacancy can be present as a single isolated vacancy, or they can also form by dimer, trimer, a cluster of vacancy.
Yeah.
So when you look at your surface, how many configurations you can find? That's the first part. Okay, not yet. That's first part of the question. How many configurations you might find in the system? The second question, since they are mainly sulfur or selenide to leave the surface, but after we grow it, let's say we do post-annealing, why they cannot be fixed? What's the things holding the problem to prevent stoichiometry?
So it means you try to fix the vacancy?
Yes, but it's difficult.
Because the vacancy already occupied by oxygen, so you cannot fix it.
But if you try to make the system oxygen free.
But if you take it out from the chamber to the environment.
Use the same chamber.
Use the same chambers? Oh.
You have sulfur in the chamber no matter
But
what.
we have some recipe to reduce the defect density. And mostly the vacancy you saw in STM not as grown. They may form during you clean your sample, right? If you sometimes your sample is too dirty and send it to UHV, you have to heat it up to maybe 300 degrees C or 400 degrees C in UHV. So in this condition, you will evaporate the sulfur or selenium. So you create your cell itself.
So that's not not possible to fix.
But in our case, sometimes we use sulfur capping or selenium capping to passivate the surface and then send into UHV and decap the surface. So it most likely close to the outgrown sample, not created by the cleaning process.
First question, defect configuration.
Configuration, we only saw single vacancy. Yeah. We didn't saw different kind of vacancy. If you have dirty sample, sometimes we will see many different kind of defect.
In one figure you mentioned that once the length goes down to below than 5 nanometer length, the mobility for silicon will goes down significantly.
Yeah.
As we heard from the news, seems that TSMC claimed that they will soon manufacture get with like 3 nanometer, maybe.
Yeah.
What kind of material will they use?
They still use silicon.
Then how they start this product?
No. I should move to this. This is a channel thickness, but when they say 3 nanometer means the gate depth. The gate depth is not equal to the channel thickness. So if you reduce down to 3 nanometers thick, so typically the gate have to reduce even smaller, maybe 1 nanometer. So in the case of so-called 3 nanometer technology, the thickness actually is much thicker. So still sad. But if you want to still scale down, it will make the problem. So the 3 nanometer means the gate depth, not the thickness. It's a factor of 2 or 3 in this case. Yeah. 是吧?
Okay. Okay, what's that, another student?
Yes, student question.
How did you know
Just wait for the microphone.
How did you know your wafer scale boron nitride is single crystal in the whole wafer? Because in your paper you said you use lead and you point nine SAED pattern on your wafer and you say your orientation are right, but in your ON image, you say you have some twin bond, you have some
Twin structures.
Yeah,
Yes.
you have some twin.
You are asking the content of that paper, right?
Yes.
Not my talk, right?
Yes.
you work hard. Yeah. So actually, we select the best sample to claim this single crystallinity.
So not every wafer are single crystal.
Of course not. Of course not.
TSMC's job.
Yeah, that's not my job. If I ask you, if you are my student, if I ask you to do everything the same, you will get crazy. Okay? So that's not possible. But we can achieve that, but we cannot guarantee every wafer is the same. So sometimes we will find some defect or some defect structure. But mostly we can achieve up to wafer scale.
So can I ask, in that very well wafer, is that lead you scan is very well in all place, or
we randomly select different place,
yes.
not do mapping for the full wafer, because we don't have micro lead facility, so we send to outside for help. So we just ask them to randomly select some position to check the crystallinity.
How about the twin boundary? Because the twin boundary will form the same orientation. Because if the SAD pattern orient about 60 degree, SAD pattern will look like this.
No, it's a 120, not 60.
Oh, my fault. Okay.
There's 3-fold, not 6-fold. 3-fold syndrome.
Okay. Thanks.
Okay, I think we have so many questions already. Okay, let's send Professor Zhang again.
戒掉，
发表 paper 的时候讲了出来。